This is a fairly old computer, not particularly fast. And here is the CPU info about it. It says Intel Core 2 at 1.86 gigahertz. I will show some details about the calibration of the frequency response for this rtl-SDR on the fairly slow computer. I am first selecting gain mode sensitivity. That is 3. And maximum bandwidth, I. Now I have set the lowest possible gain, and then I see an amplitude margin of 46 dB. This isn't useful at all, but I start here to show what it means and what happens when I increase the gain. I can run the mode I, what is it called? Sound card test mode. It isn't a sound card, but it is input. And here, and I have to expand. And you can see that mostly the value is the same, and occasionally it is 1 bit up. And obviously this isn't going to be reasonable for the noise floor, and it's not reasonable to do calibration here either. So first I increase the gain here until I start to see noise. Well, maybe something like this. And then I look at the amplitude margin. It's now at 37 decibels. This is a pulse generator generating pulses. I don't remember exactly, but short pulses with no oscillations, just a square. I think it is something like 5 nanoseconds or so. And I can step the signal level with this stepped attenuator. And I increase now, looking at the amplitude margin. I clear it. It says 37, and I go up here. And now it's 22. And now it's 12. That was a 10 dB step. And I'll change here so I can see. And then another 10 dB step. Sorry. And it is now compressed by about 1 dB. It didn't go from 12 to 2, it went from 12 to 3.5. So if I back off in steps of 1 dB, 1, I go back. This is less than 1 dB, and 1 dB again, and 1 dB again. Here it is about 1 dB. And then I see a margin of 6 decibels almost. I can increase the level in steps of 1 dB from here. And you can see it doesn't increase by much, but it does increase more than expected, as seen from the amplitude margins down here. But now it goes the other way. I'm still increasing. And now I add 10 more dB. And you can see the shape, the frequency response is different. And these are 1 dB steps back, then 10 dB. And now I'm increasing more the signal level. And of course, these things are due to the saturation of the front end. And the unit is heavily saturated, and this isn't very useful. I just wanted to show it. So this is 37 dB amplitude margin, and I show what is the input here. That's I, and increase the gain. And you can see it is just 2 levels, and there are occasional dots here. So it is RMS about half a bit or 1 bit or something. Not much, but it is at least some noise. Now I select gain mode 2. That is the linearity mode of Linrad. And the same bandwidth. And of course the same. And enter. Sorry. And I want to have the same amplitude margin as before. So I reduce the gain here. And one more step. Here. Now the noise floor is the same, and I add the pulse generator. And here it is weak enough, and I add 10 dB, and it's almost 10 dB, and I add 10 more decibels, and it is 9 dB, so I can look here while I go back in steps of 1 decibel. And I go up again. This isn't quite 1 dB. So it is something similar. I didn't look too carefully about where the compression started, but it's we have to remember there is some accuracy issue also with an attenuator like this. But it looks like it is still compressed. And that indicates that this gain mode is less favorable when I'm trying to calibrate with this wideband source. So I give it a try, and I try a little bit more signal. If you look at the shape, it is sloping a little bit more here than it is here. So some kind of compromise. I try to correct for this frequency response. Calibration, that is X, and calibrate, and I am going to do the total amplitude and phase, that's B, and press enter. And it isn't quite okay, and now it fails. The problem causing this false response can be seen if I go here for which one is it? System and system monitor here. And it says CPU is around 90%, 80%. It is a very high load on the system. Now, of course, this system monitor adds some extra 4% or something. But there is an overload issue. So what I do here is X and then global parameters, that's S. And I go as before. I don't want to block any. Screen size, and I don't remember, let's say 77 by 77. And process priority, I set 2 here. It was normal before. Are you sure? Yes. And no auto start. And of course I have to save this and then go for the SSB mode again and calibration, and that is C and B and enter. And hopefully it works better now. And indeed it looks so. And that's because this is not a fast computer, and 2.4 megahertz is a fairly high sampling rate. So I accept this as the calibration. That means U, and I take standard, means accept this, yes. And then, oh, it doesn't like this, but I save it anyway. And it looks okay here. So I don't know what was causing that. Errors occur now and then. So here is the calibrated frequency response. And we can see how the pulses look a little bit extra ugly now. That's because of the steep fall off on the sides. I can use the smart noise blanker here. And then this is what remains of the pulse. And of course I can use the dump blanker also to clear those few points that were a little bit high. And if I use only the dump blanker, you can see it makes a much bigger gap. Means there are much more problems that this gap in all the strong signals that may be in the spectrum will cause keying clicks. Now Linrad is a little bit more clever than that, so very strong signals are not, the blanker doesn't operate on them. But anyway, there are advantages with this smart blanker, and there could be advantages of using both of them. So I disable the blankers again, and now I look at the very flat curve I have and change the level of the pulses. 10 dB weaker. And this doesn't look so nice, but if I switch off the pulses completely, you can see this is the noise floor. Pulses are not so strong when I reduce by 10 dB. So I increase by 10 dB again. This is of course depending on the repetition rate of the pulses. And I go up 1 dB at a time. That was only half a dB, and again half a dB. And now I go up 10 decibels, and here things fail badly. Of course, the front end is completely saturated now by those very strong pulses. So this shows some limitations of the system I have now, because the front end is wide open for these very wide band pulses. So things before the IF filter, which is actually a low pass filter for I and another one for Q, things in front of the IF filter are saturated. I have inserted this box between the pulse generator and the attenuator. This box has a bandpass filter that converts the pulse to a pulse train, damped oscillations with a duration that is the inverse of the bandwidth of that filter, in the order of 10 megahertz or a little bit less perhaps, I don't remember exactly. After that is a Class C amplifier that converts the damped oscillation to a pulse train. And when the oscillation goes below a certain level, the Class C amplifier is completely silent. So this gives a narrow band signal, far less prone to saturate the wideband input. Best seems to do calibration in the sensitivity mode, number 3. And with a larger bandwidth than default, I have set 1 kilohertz here, and the rest is the default. With the gain set to 38 dB, the amplitude margin is, well, 34. It varies a little bit, so I reduce this one step, 32 dB, and it now says 39 or 37. Of course, there is a statistical variation, so this can be the appropriate gain level for doing the calibration. I switch on the pulses, and here, and this is with an amplitude margin of 6 decibels, and I add 1 dB. That seems okay. 1 dB more, and I've got 0.8 decibels this time. Well, and 3. And here, this step did not give 1 dB anymore. I give it 1 more. And here it is saturated. So I back off those 2 dB, 1, 2, and clear. And it seems I need to have an amplitude margin of 3 dB to avoid saturation in circuits in front of the AD converter, inside the dongle. And I will do calibration here. So here is the screen, the first screen of the calibration, and I press enter here. And now Linrad is collecting the average pulses in the Fourier form. And it runs rapidly. That's because I set this bandwidth of first FFT to 1 kilohertz. And 13,000 pulses is plenty. So U for update. And I don't want as sharp edges as there are now, I can change the shape form with M. This is now a parabolic fall off, and I don't want it to reach all the way out to the edges, so I make the flat region smaller. That's B. Maybe like this. And then accept by Y. And for some reason this doesn't provide good pulses. I can ignore just to look at what it looks like, and it doesn't look bad except for this thing, which was caused by a spur. Here is now what I see with the pulse generator on. The structure here is not as ugly as before, because the fall off is much softer. I can enable the smart blanker, and not much remains. I can increase the gain of the time function here to see those remainders better. And of course with the dumb blanker also, like this, very little remains. And I can make the dumb blanker a little bit more aggressive to obtain this. I have increased the gain now to have a reasonable noise floor. So now quantization noise will be low. Of course, this noise should originate not from the dongle as it does now. It should originate from the antenna and the first preamplifier. But for my evaluation, this noise is good as any other noise. And now I add the pulses, like that. And as you can see, it is almost saturated, or it is saturated, so I reduce the level a little and clear. Well, once more. Here I have saturating pulses, and they don't look too bad when you look here, but if I change the mode and click on L here, you can see what it looks like, and it looks good. That's because I have the clever blanker enabled. I disabled that, and here are the pulses as they look now, and you can compare to the noise floor the level of these interference pulses. I can reduce the gain. It is 0.5 now, a factor of 2, 4, 8, 16, 32. So it's about a factor of 32 in amplitude, the noise and the pulses. 32 in amplitude, that is 1000 times in power, so it's 30 decibels. But that is the peak amplitude of the noise, of course. I look at, let's say, 144.1, that's here, 144.1, and here is the noise level without the blanker. And I disconnect the pulses to look at the noise floor. And I have calibrated for the S-meter to show 0, 0.018. That's close enough to 0. And I add the pulses, and you can see it is about 9 decibels. And then I enable the smart blanker, like this. And now it is very close to the original value, but not quite. probably. It's 0.1 dB, the difference. So 0.1 dB of interference is still present. I save the calibration function because the next step can go wrong. That is C, remove the center discontinuity, and the region near the center now is 2.3 kilohertz excluded. That's not enough with the high repetition rate I'm using. I remove more, let's say 6 kilohertz. That is L and 6000. And then continue. And here we see the yellow is the raw data I have. And I expand the scale. And red is the difference between the computed function and the raw data. And as you can see, the red is flat from here approximately all the way out. There is some noise. So I don't want this spur and I don't want that spur. So I move, what do I press? I move L. To this point, which means starting from here, I will use the fitted curve instead of the raw data, which corresponds to make a straight line here. That will remove, I will have this curve without the spurs and also without the noise. So I press A to accept this, and here is the next, and it's clear that the red track is a straight line on all frequencies, so it doesn't matter at what point I start to use the fitted curve instead of the experimental. So I just accept this A, and here I have a spur here, but the curve looks fairly flat. I can try with fewer terms. It's 6 now, I make 5, 4, 3, that's not so good, 4. Looks like this would be okay. So I move to the right, to the left, to eliminate that spur, and from that point where it starts to become 0. So accept. And here I have only 3 terms, so I try 4, 5, 6. Well, so I use the raw data up to this point where the blue line is now. Accept. And here is the new calibration curve, which doesn't have the problem at the center and which doesn't have the spurs I had before. So I save this, and that is a little bit risky, so let's see what happened. And this went okay. The smart blanker is still doing well. I have disconnected the pulse generator and waited a while, and also changed the calibration just a little. It shows 0.03 now, and I connect the pulses. It was at this point in time, and I have to wait for a while to see. It isn't visible by eye, but maybe it is a little bit more noise from here to here. 0.03 dB. So it's really rather successful, and it's only the smart blanker at this time. Since it went well, I save the new function again to the directory sav that I have below the DSP directory, because the next step could also go wrong. And that is D, refine amplitude and phase correction. And here you can see by the number of points I'm using how much information is lost, and it seems like I don't need more than 64 points at maximum. So I don't save it in 128 as Linrad suggests. I save in 32, so I say no, and 32. Yes, and then we will see. And yeah, it looks similar. I don't think I lost anything. Here I'm playing a 1-minute recording made by Jim WB9UWA. He is turning his antenna one turn in azimuth, and I'm playing the recording over and over again. So this is 360 degrees, and then it starts again and again. And you can see the S meter, it repeats, of course. And I'm listening on 144.2 with a bandwidth of maybe 12 kilohertz or so. And you can see the pulses that come, sometimes quite frequently. There is no calibration, so I can only use the dumb blanker, and I enable it now. And the number of cleaned, removed pulses is the number here. It's 1%, not very much, but it can go much higher. It does have an impact on the waterfall if you compare this region with what we see here. But removing as much as 5%, well, that's not really very much. And as you can see here on the S meter graph, this part and this part, the improvement is about 5 decibels. And it seems this peak has disappeared. The setting is rather aggressive. You see the distance from the yellow line to the green bar, which is the noise floor, is not very large. But I don't have the smart blanker here, as you can see. And if I try to make the blanker more aggressive by moving this down a little, oops, in automatic mode it's a little bit difficult. Now, as you can see here, it is a bit closer, and the number of removed points, the percentage of removed information here, if it becomes very large, we are removing also signal. But the noise floor looks better now, and here on the main waterfall it looks much better. Here is the unmodified power spectrum, it is like before, but the waterfall is on a signal on which the blanker has been applied. But here we are up at 10%, 12. This could be too high, but it could also be okay. That depends on things that I don't know. There is no useful signal at this time. The antenna is turning around, so there couldn't be any useful signal. Now, this is uncalibrated. Jim has provided a recording with pulses for the purpose of calibration. But this doesn't work well. There are two strong spurs and the noise floor is low. You can see it better maybe here. So I tried a calibration, that is X and C and B. And here we can see the pulse. And I press enter. And signal to noise ratio is not good enough, but I ignore, means try anyway. And Linrad doesn't collect any pulses, it just increases spur. It means pulses that are with spurs in them that Linrad cannot manage. But there is one thing I can do here. I can say clear run, that's A, and then save. And that's X. And then I go for the processing again. That is 3, and the recording was 1. This one. And now I'm running without the blankers. There will be no difference at all. So I wait for a while to get the screen filled. So now I have 2 periods here, and I will enable the smart blanker, because now there is a calibration function. It's just flat, both in frequency and phase, but it is there. So like this. And as you can see, there was some improvement. And if we look at the... I'll wait for a while to see what happens here in the waterfall. It's clear there is an improvement. You can see from here to here. It's not as big as it was with the dumb blanker, but now I can add the dumb blanker also. Like that. And it removes now many %, but not as many as before at this very aggressive position. So I wait for a while now. It is most of the time below 5%. It can go up to as much as 12 at the worst point. But you can see here it looks significantly better than it did before down here. I will allow it to run one more period, and I will disable the blankers in this point. To get a fresh picture of what it looks like without the blankers to compare with the blankers in the waterfall as well as in the S-meter graph. And you see all the pulses here, and this pulses come so frequently that with a 64 kHz sampling rate they will not be distinguished as pulses. It will just be random noise. But Linrad can resolve this. Not well, because it's not calibrated now. It could be a little bit better than this. And of course the dongle has a very limited dynamic range, so it is not perfectly sure that this is going to be so useful. But the potential for improvement is in the order of 5 or 8 or maybe 10 dB. And you can see here now I have applied the calibration function I made from my own dongle, the first part of this video, and I'm playing the recording made by Jim on his system, which is significantly different, and you can see from the spectrum here that the curve isn't flat, but it is looking reasonable. Anyway, here is the S-meter graph and the waterfall, and the number of removed data points by the dumb blanker isn't very large. So it seems a little bit better than the just flat calibration that I made by clearing the memory and saving the not so good calibration function that I had. So for a comparison, I will disable the blankers now, so you can see the difference on the curves. And 144.2, that's where I'm listening. It is dark blue or black, but here it is green. So there is a difference, and on the S-meter it is from here. Well, I try to get the same region in time. It is probably here. Sorry. Here corresponds to here. So it is 8 down to 2. It's about 6 decibels. So there is an improvement, but still there is a lot of interference. And the pulse repetition frequency is really quite high. And many not so strong pulses.